Morning, everyone.
Good morning.
As you know, today is our Q&A session, open to your questions and answers, or actually your questions, and then I'm supposed to provide answers. So that'll continue as long as you guys have questions. And we are recording it, so I'll try to, post it later, unless there's, too much copyright content or something like that. And if there's a little bit, I don't worry too much because I don't think, the 12 people that are looking at my YouTube channel is a problem. Anybody have any questions for us to get started?
I had a question on the the practice funnel.
Okay, go for it, Kobe. Actually, let me sit up so y'all can share screen if you need.
Well, I can't because I'm on my tablet again. Because
Gotcha.
Yeah, but it says the position vector of an object of mass 0.5 kilograms subject to a constant force is given by R equals AT squared plus BTI plus CT squared plus DTJ plus ET squared plus FTK. Where A is 2 meters per second squared, B is 3 meters per second, D is -2 meters per second, E is 1 meters per second squared, and F is 4 meters per second.
Okay.
What is the angular momentum?
What is the angular what? Acceleration?
What is the angular momentum at T equals 2
momentum.
seconds?
Okay. So they've got a position part, and you said it was a particle, right?
All they say is it's just the position vector of an object of mass 0.5 kilograms.
Okay. Well, in that case, since it's an object and they said it has a position as if it's just one single point, you can either assume that they've given you the center of mass, the location of the center of mass, or you can assume it's a point particle. Either way, the R points to it. So what we know is the angular momentum is R R cross V. Okay. Or excuse me, R cross P, where P is momentum, mass times velocity. So they gave you the mass. What you want to do is take that R, and then you're going to take the derivative of it, and that'll give you the velocity.
And then find the velocity and
multiply that velocity times the mass, and then you have a new vector, and then you cross product R in the second line of the matrix and mass times velocity in the third line of the matrix, and do that determinant, and you'll get the actual angular momentum out as a vector.
Thank you.
Does that make sense?
Yes, sir, it does.
Yeah, and I wouldn't put those numbers in until the end because it's a lot easier to take the derivatives with A, B, C, D, E, and F than it is with all those numbers and units floating around.
You said that it's R cross V?
It's R cross MV.
Oh,
and remember, when you multiply a scalar times a vector, the M just goes in each of the components.
All right, that makes sense. Thank you.
No problem. Anyone else? David? Or David?
I got a couple questions.
Go for it. David, number one.
I'm going to share my screen real quick. Okay, can you see my screen?
I can.
Let's see here if I can get my, there we go. My little Zoom bar was in my way.
Okay.
The first one is on chapter 43 conceptual.
Okay.
First question, I have everything else in the conceptual except for these first two parts. I don't quite understand.
Okay, let me read the blue part first. It says in elementary particle interactions, there is a set of conservation laws governing all interactions. These laws include conservation of energy, momentum, charge, baryon number, and lepton number. There are other physical quantities that are conserved in some interactions, but not in others. Consider the production of a muon pair by colliding electron and positron beams at the Stanford Linear Accelerator. The energy of both beams is 3 GeV, and the collision exactly head on. What are the total momenta on the left and right sides of the equation? Okay, so this is a case where E squared is equal to P squared C squared plus M squared C to the fourth. So you can
what was that again? E squared equals...
E squared is equal to P squared C squared plus M squared C to the fourth power. That's the total energy. So that's something we might use. But right now I'm thinking we're probably just doing the momentum. So it shouldn't be a problem. But just remember that other formula in case we run into problems. So right now we can calculate the actual momentum of any particles because they gave us the energy as 3 GeV. That energy is just the kinetic energy part.
Okay.
So you can say, actually, let me write this stuff down a little bit. And then, so I got 3 GeV each. And I've got electron, positron yields a muon, positron, or excuse me, anti-muon. And they want to know first P initial and then P final. The next question is, the mu plus was observed to have 1.5. So mu plus 1.5 GeV. I think that's what part B said, right? Yes.
Yeah.
What is the energy? What is the energy of E mu minus? And that's it. And then the third part, if only the mu I detected, which
I
statement
got the
best?
third and the fourth.
Okay, so those are more. Okay, you can do get those. Okay, so I've got that written down. So what I'm going to do is I'll steal the screen from you for a second.
Go for it.
And so we have some expressions. One thing that you might need, we're not sure yet, E squared is equal to P squared C squared plus M squared C to the fourth. Okay, that's the total energy. Whoa. Evidently total is spelled with a P now. The total. And this part right here really is the kinetic energy part. But we also have the formula K is equal to gamma minus 1 MC squared, and P is equal to gamma MV. So those are all things we can make use of. And in fact, stuff like the electron and the positron, we know M E plus or minus C squared is equal to 0.511 MeV. So we know that quantity already. And you can look up the same quantity for mu plus or minus. In other words, they actually times C squared. They normally list it as MeV per C squared is what the mass is. But you can just write it like this, MC squared is equal to that. And then that'll allow you to just use units of MeV. So C squared is equal to something like that. So you can get that number. Now the still not in focus very well. I don't like that. I guess that's a little better. My cat keeps coming up here and redirecting my camera, and then I bump it and all sorts of good stuff. There you go. Okay, so those are the main expressions we need. And what they're initially asking for is what is the momentum of the two particles before? Isn't that what part A was asking for, David?
I believe so.
Okay, so what we want to do is we want to do gamma times MV, and we already know that we can solve for gamma by just saying 3 GeV is equal to gamma minus 1 times MC squared. All right, so 3 GeV divided by 0.511 MeV is equal to gamma minus 1, or gamma is equal to, now I'm going to convert this to MeV. GeV is 10 to the 9th, MeV is 10 to the 6th, so this is 3,000. So we can do that. And I'm going to do 3,000 divided by 0.511. So it should be around 6,000. And that is in fact that plus 1. So that's actually gamma equals 5,870 1.8. So that's what gamma is. So we got the gamma factor. And of course, we could also use that since we know gamma is equal to 1 over the square root of 1 minus v over c squared. So we can say square both sides, that be gamma squared is equal to 1 over 1 minus beta squared. Notice, remember, v over c is just beta, so it's easier to write beta. So now I'm going to say 1 minus beta squared is equal to 1 over gamma squared. And then I'll say that beta squared is equal to gamma squared over gamma squared. In other words, I converted that 1 to have a common denominator already, minus 1 over gamma squared. So beta is equal to the square root of gamma squared minus 1 over gamma. So now that you have that, you can compute basically the factor that's in front of the c when you talk about the velocity. So if you said 98.9% of the speed of light, it'd be 0.989 would be the beta. That's what pops out of that.
Okay.
So we can take that, I'll say.
Couldn't you, if you're calculating the momentum, couldn't you just use the gamma in your momentum equation?
Yes, but notice you still have to have the velocity.
Oh, you still have to have v.
Yeah, if this was MC squared, it'd be a lot easier. So yeah, I just squared this 5,871. Actually, I should take parenthesis. I need to add the 1, even though it's pretty darn small, but control answer plus 1. And now I'm going to square that. And then I'm going to subtract 1. And that gives me, under the radical is about 34 million. Okay. And now I'm going to take the square root of that. And now I'm going to divide it by that same number. I got to remember to add 1. So I went back up there and did that. Let's say enter. I'll say plus 1. Okay. Whoa. So I get beta is darn close to 1. Let's say I got to read on my calculator exactly how close it is. Oh, crap. That's really, really close. So it's like 0.9999999. So that's like 7 nines. Uh, 8.5. So that's what beta is. That's kind of a problem, right? We're really getting really close. But the good news is we're actually approximating this being 1 is approximating the regular momentum. So now I just have to multiply that by the mass of the electron times times that velocity times c. So I'll say this number times the mass of the electron. We can actually MEV per c squared is actually the mass, but MEV per c is actually the energy. What units did they have for the, is the momentum? What units did they have for the momentum? Did they have MEV?
Giga electron volts per c squared.
Okay. Per c squared or per c?
No, just per c. My bad.
Yeah, okay. So right. So what we're going to do now is we realize that P is equal to gamma m times c squared times v over c squared. Notice if I multiply by c squared in top and bottom, then everything works out fine.
Yeah.
So now I've got the exact same thing. So now I can take gamma and multiply it by 0.511 MeV. That's that part. And then I've got V over C. Part of it's just beta. And then I can do beta over C because V over C is beta.
Okay.
So now I can say this god awful number times 0.511 times 10 to the negative third, because they want GeV. And
Okay.
then times beta. Oops. Well, I actually did the beta already, so I got to do the gamma. 5,871.8. I did it in the opposite order. This is beta. This is gamma. This is MC squared. And now I need to multiply by what? I need to basically beta over C. Normally I would want to divide that by C. So this right now is giving me units of gamma electron volts, but I want gamma electron volts per C. So I don't want to really carry out that. So what I'm going to do is I'm going to take that C and put it under here. And that's good because that's exactly the unit I want.
Yeah.
So that's how you work with that C and C squared in the case of energy and C in the case of momentum. So now I want to take that answer, that 0.999 whatever, times 0.511 e to the negative 3 times 5871.8. And that gives me 6.000 even times, or excuse me, GeV per C. So that's the actual momentum of the electron. Of course, the positron is exactly the same. So it should be 6 GeV per C in both cases, barring some stupid arithmetic error.
I submitted 6 GeV before, and it said it was correct.
Did you do 6 GeV comma 6 GeV?
I did.
And let me see the question again, make sure I'm reading it properly.
Yeah.
Okay, and oh, wait a second. That said P initial and P final. I thought it asked for the initial of each of those. So the energy of both beams is 3 EG, and the collision is exactly head on. What are the total momenta of the left and right sides of the equation? Oh, okay. So it still wants 6 and 6 would be 12 here. And that's got to be 12 on this side as well. So it should be 12 and 12. What the crap? So we saw the calculation. This gave us 6. Oh, wait a second. That's stupid. The energy of both beams is 3 EG, and the collision exactly head on. What are total momenta? What frame are we in? I wonder. Are we in the center of mass frame? I think we have to be in the center of mass frame because you're directing the two beams at each other.
So then it would be 0, 0.
Exactly. Now let me. You want to submit that? You got enough chances, right? Or are you losing points each time?
I do lose points. Let's see our previous answers, because I think I said 0, 0 before, but let's make sure.
Yeah, I don't want you to waste that.
Oh no, I didn't say
Yeah.
0.
If you want to, I can double check, make sure that one's right before you submit.
Oh, that's okay. We'll try it.
So a lot of this turns out to be, can you read the question properly? Which obviously your instructor can't, but luckily I made it through the class already. Sucks, don't it?
Oh no, that's all right. Yeah, 0, 0.
Okay. Yeah. So what's going on there is you have a beam going to the right and a beam going to the left, which is actually the exact opposite of what I just showed with my hand. So a beam going to the right and a beam going to the left. They're identical particles except for their difference in charge. The E minus and the E plus So they have the same mass, they have the same energy, therefore their momentum would be the same, but this one's momentum would be positive, that one would be negative. That's why that's 0. And then of course, conservation of energy is always going to be in effect unless there's a net force acting on them, and there's not. So the other side has to be 0 as well. That's why that worked out. Does that make sense?
Yeah, that makes sense.
Now, part B, it says the mu plus was observed to have an energy of 1.5 GeV. Okay. So what is the energy of the mu minus? Well, conservation of energy would predict that basically the total energy you had before the collision has got to be the total energy after the collision. But what do you think the total energy is before the collision?
Total energy would be greater than 6 GeV because you have the rest energy of the electrons.
Exactly. And then after, notice it's going to be the kinetic energies, the sum will be less than the kinetic or the total energy before, because you now had to take that mass that was destroyed and actually increase it. Because remember, I told you the muon weighs about 207 times heavier than the electron.
Okay.
So the total energy has to be the rest energy of the electron, the kinetic energy of the electron, the rest energy of the positron, the kinetic energy of the positron. So the total energy before would be 0.511 MeV plus 3 GeV plus 0.511 MeV plus 3 GeV. And then the same thing over here, except it'd be MC squared plus its energy. And then MC squared, which is the same as that one, plus its energy.
Okay.
So let's try to work that out. So we said the mu plus had a energy of 1.5. Yes. Okay. So E initial would be 3 GeV plus 0.511 times 10 to the negative third GeV. Remember, that's MeV, so I had to make it 10 to the negative third to make it a GeV.
Okay.
Plus 3 GeV plus 0.511 times 10 to the negative third GeV. That is equal to 6.001022 GeV. So you see the rest mass of the rest energy of the electron is pretty insignificant compared to the whole thing.
Yeah.
The energy in the final has got to equal, let me look that up right quick. Did you look that up already? Do you know what the rest energy of the muon is?
No, but I should have it in my notes. Let me.
Okay. I think it's going to be 0.105 GeV.
Here. I have 105.7.
There you go. So this should be, and that's MeV.
Yes, sir. Mega electron.
So it'll be 0.5117 GeV
Okay.
plus the E of the mu minus plus 0.511, or excuse me, so the plus one's the one we don't know, right? No, it's the minus one.
I must have misspoke because I think the rest energy would be 0.5017.
Okay, gotcha. I think that was me just pushing that answer in there because I made that mistake when I did it.
Actually, I think I missed 0.1057.
Oh, okay. So this is 1057.
Yeah. So I misspoke twice.
Yeah, well, it might have been my fault because I had already told you it was like 0.5011, so it probably screwed you up between what I said and everything else. So 1057. You can see that is quite a bit larger because this is 0.000511 for the electron, and that's literally almost it's actually 207 times bigger. So in this case, you can see this one has 1.5, this has 0.507. So all you have to do is say 6.001022 equals 1.5 plus 0.2114 plus E mu minus. And that should give you E mu minus.
Okay.
So I get E mu minus is equal to what, 4.2896 GeV.
Let me check.
They probably only want 4.3 or something like that.
I got the same answer.
Okay, well, that gives me some confidence. There shouldn't be anything else we're missing, but that should give us the energy of the muon afterwards.
Let me plug that in.
Yeah, let's look at the question too before you do it again, just to make sure I read everything properly.
Okay.
Don't want you putting in the wrong answer because I gave you the wrong answer. So it said the mu plus was observed to have energy of this. What is the energy of that? Okay, so yeah, I think it's 4.29. That should be right. And it did say 1 decimal place, so you should write 4.3.
Okay.
It's not submitting it, is it?
It says incorrect.
You get 5 originally, or you get 4?
Yeah, we get originally.
Okay.
So I tried spinning it again, and
Yeah, it seems like it didn't take that second answer.
DJ, what was the unit for the resting energy on your notes, real quick?
The rest energy.
Yeah.
I had 105.7 mega electron volts.
Oh, okay, yeah. Yeah, because with how I heard originally, like okay, yeah. So it would be .1, whatever.
I'm gonna double check that too, just before we submit again.
Yeah.
So I'm looking on a table, try to find it there anyways. So the muon, of course, it's not in that table. That's always helpful. Never can find a table I want. Oh, there it is. Okay, so the muon, yep, 105.7 MeV per C squared is the muon. Of course, that's the same as the the anti-muon. So yeah, you got all that right. And I didn't think it submitted that. What did it show you for your previous answers? Because I think it only took one of those. It looked like it to me. It looked like it only took the first one. Is it locked up or something?
There we go. Can you see? I probably need to share it as well.
Oh, it's got a pop-up window that showed you the previous answers.
Yeah, there we go. Can you see that?
Okay, so it did say that was wrong. Wow. and maybe even twice as wrong. All right, what I'm gonna do is I'm gonna check something real quick, make sure I didn't miss anything. And I'm also gonna make sure they don't have an error, because that is actually a real possibility. These systems are, they always have errors in them some way or another. And that usually comes from changing from one version to the next.
Yeah.
So I would check that right quick. That's odd. Anybody else find an error on that? I did 3 GeV and 3 GeV and 0.511 times 10 to the negative 2 GeV. Make sure when you add 3 GeV and 0.511 times 10 to the negative third GeV, see if you do get 6.001022, just in case that might be our error. And I'm going to try to pull up this.
Okay.
You said this is in the conceptual?
Yes, sir. It's the first question, chapter 43, conceptual.
Okay, still piddling along, looking. I'm getting there slowly but surely. Computer's going slow, sorry.
Well, so for the E initial,
Mhm.
you have both the electron and the positron.
Right.
So I think it would be 2 times 6.0010.
I think my 6 was already taking that into account, because I had, what we did find was 6 GeV per C for the momentum, but the energy was just 3 GeV. So that might be.
Oh, yeah. Okay. Yeah.
Yeah, I make that same mistake all the time. It's the only reason why I've picked up on it. Okay, 43 conceptual. Well,
yeah, I got the same initial energy.
Got you. Did get that 6.00 something.
I got 6.001220. 0122.
Gotcha. Well, this is weird. I went to a class, my morning class. You're not in my morning class, are you, David? You're
No,
not.
No.
Okay, that's weird. That homework set doesn't exist in my morning class, so they must not have got that homework set. So I had to go to another class now. That was weird. They're supposed to be copies of each other. So much for
Hey,
that.
Professor, I guess I'm gonna head out.
Okay, if you have a
Thank you
question,
for
I can
answering
answer
my
that real
question,
quick
though.
for you. Did you have a question before you left?
You already answered that. It was, I was able to work it out. So
Okay,
thank you.
cool. No problem. Thanks for coming, man. And David, you just say you're the 545 class, right?
I take the 12:30 to.
Gotcha.
Like
yeah, you're my Chesapeake class. Gotcha.
Yeah.
I just want to make sure I went to the right one, so I didn't waste as much time next time. And who knows if it's in the other class or not.
Yeah.
All right, now it's pulling up. It's working a little faster now. I don't know why all of a sudden. Still not impressive by any stretch of the imagination. There you go. Oh, I found it. I'm going to make sure they don't have any obvious errors, and then hopefully find some obvious error that I made, but I don't see anything wrong with this whatsoever, unless I, again, misread the problem, but read it several times now, so I think I haven't misread it this time.
Yeah.
Okay, so it looks like this is not an algorithmic problem. Oh, I think I see what happened. .211. Oh, okay. We're actually more right, to be honest with you. Let me show you what they expected us to do. Because
Okay.
this is 0.211, if you ignore the rest energies of the muons,
hmm
6 minus 1.5 is 4.5, and that's what they want. So our answer is more correct. But they were saying, hey, this is 0.2 out of 6, so we should throw that out. I wouldn't have done that. I certainly would have thrown out this one. That's not a problem at all. And I only did it to be pedantic. But these two, they decided to throw out. That's why they got 4.5 instead of 6. I mean, instead of 4.3.
Okay. So the two, I just want to make sure I also understand this conceptually. So you have two beams of electron, each one with a energy of 3 gig electron volts.
That's the kinetic energy, yes.
Yeah, yes, sir. The kinetic energy.
Right.
They collide, create a muon and anti-muon pair.
Right.
And one of the muons has an energy of 1.5 gig electron volts, and the other one has a kinetic energy of 4.296 gig electron volts.
Right. And they're rounding off that 0.2, basically. The 0.2 in there, they rounded that off and just said, so now they have, instead of 4.28, which is actually more correct, they're just saying you have 4.5.
Okay.
So the right answer that they want is 4.5, which, like I said, I would not have played that loose. I mean, 0.3 out of 4 is what, 3 out of 40. So that's 3 times 2.5 is 675. That's 7.5% error. I don't think I would have just thrown that out there. But yeah, so now you know what the right answer is anyways. But that was weird. I'm surprised. I'm not surprised that they'd throw out the rest energy of the electron, because that's obviously, way too small. That's why it's way over here. But this guy right here literally comes up to the first decimal place exactly where they were asking for it.
Yeah.
Yeah, so that's just a little reckless on them. It might have been one of those things where they went from one addition to the next and they changed the particle from something that was lighter to the electrons.
Yeah.
To the muons, sorry.
Does that mean that one muon's traveling faster than the other?
Yeah, one will definitely be. So one's got 4.5 GeV of kinetic energy. The other only has 1.5 GeV.
Well, if you have two particles, your electron and your positron, which have equal mass, hit each other with equal energy, how would one end up traveling faster than the other?
Yeah, by symmetry, that would not be a likely conclusion. But what they did is they forced that answer by saying it's 1.5 is one of them. And, they didn't have any choice at that point. If one of them's 1.5, the other one's got to be 4.5 or a little bit smaller.
Oh, okay.
Yeah. So I think if you did 1,000 of them, probably that equal split would be likely. It would be exactly right, where you'd have 3 and 3. But in this case, they didn't, because they forced it to be 1.5. But that's exactly the kind of thinking you need to do as, a physics student.
Okay.
Is there another part of this that we need to figure out now?
I have a couple more questions, but if David has some questions.
Yeah, David, you have anything? David Parsons?
As far as like specific like test questions, I don't have. I just have like one like concerning the like final test. That's
Okay.
really it.
Okay. Did you want to ask that?
Yeah, sure thing. So I know that you said like for the in-person test, like you only have to answer like 12 and you'll take the worst 12. Something along the lines of that.
Yeah, if you do the 14, I'll take the worst 12. So just choose 12.
Yeah. How much
ahead.
would you take out of the online?
It's the same thing, both of them. Yeah, and in fact, if you want to, I'll try to put in a blank in there somewhere where you can type something in. So if you accidentally filled out all 14 but couldn't, go back and erase the other 2, because if you accidentally select one and then change your mind, you can't unselect it. It's going to have to have an answer from there on out. So I'll try to put a question in there where you can say, just before you turn it in, you can submit, by the way, I wanted number 8 and number 11 to be omitted, but I couldn't undo them. So I'll fix that. I just thought of that when you said it. I think I can fix that, and I'll try to give it a try.
All right.
If
So
not,
it's
you
the
can even see it
worst.
on the video.
All right. So it's the worst 12 for each test.
No, it's just the 12 that you choose, period. It's only the worst 12 if you turn in all 14. In other words, I'm trying to
Okay.
encourage you not to turn in all 14.
All right. Okay.
Right. You see what I'm saying? So go with your what you think is your most confident 12 and don't answer the other two. And in fact, don't answer any of them until you've decided what the confident 12 is. Because if you select an answer that you later want to unselect, you won't be able to.
Okay. Yeah. That makes sense. I was just curious mainly for the online test because there was like 22 questions. So I'm like, wait, that kind of like you're only taking half the test if that was the case.
Yeah, no. If I'm remembering correctly with your class, I gave it's supposed to be 14 problems, choose your best 12. But if you don't choose your best 12, you actually turn in all 14. That makes a bigger grading problem for me. So I'm doing that to get you not to make my life more difficult.
Okay.
That's all.
Yeah. I was just like looking at it because like I can kind of see the overview of the final already, and it
Mhm.
says that the online's 22 and the in-person's 14 for whatever reason.
Oh, okay. Well, thanks for catching that. I'll go back and check it. It might be something where sometimes a stupid thing will embed a couple different tests together. And obviously I don't want that. So I'll check that out now. What are you in this class this morning too? Are the two 12:30 classes today?
Yeah, I'm in a 12:30 class today with DJ and Colby actually.
Gotcha. All right, I'm going to check that right after we get out of here so I can make sure. I don't want it to be bad on test day, that's for sure. And it might be
exactly.
I'm really concerned because I thought I did like 22 on my 242 class and 12 or 14 pick 12 on my 241 class. So I could have done something as stupid as put the wrong one in there. So thanks, you saved me something here. So I'll get that straightened out. But no, they're not different tests, whether you take the online or the testing center one.
Okay.
Not supposed to be.
All right. Well, that sounds good, I guess.
No problem. Are you you're taking face online, right, David?
Yeah, I'm taking online.
Yeah, that's cool. I had one student, I think it's Colby, that's doing the face-to-face at the testing center. And if he was taking it at a different time, I'd have to make him up a different one. But he's supposedly taking it at the same time you guys are.
Okay.
David, Caleb, you got another one?
I do have another one.
Go for it.
Share my screen.
Mhm.
So on the go
The
ahead.
first antiparticle, the positron or anti-electron, was discovered in 1938. Has been predicted by Paul Dirac in 1928. Though the nature of the prediction was not fully understood until the experimental discovery, today is well accepted that all fundamental particles have antiparticles. That's correct. Okay. I'm trying to make my screen bigger. Let me figure out how to do that real quick.
Oh, I can zoom in. Here. Or
Okay,
maybe
yeah, gotcha.
I'm
All
missing
right. So you did part A, B, and C. Okay.
Yes, sir.
Okay, let me look at
are all
those real
good.
quick so I can get an idea what they were asking. So which of the following are different for a particle and its antiparticle? Yep, the charge, that's good. Sometimes there, by the way, there are other numbers that change. They didn't happen to list those, but like baryon number and that sort of stuff. The antiparticle and the particle change, the baryon number changes for those, as well as the lepton numbers. So just keep that in mind,
Okay.
even though everything you wrote there is right. What's part B say? Which conservation law is violated by particle antiparticle annihilation? Yes, there shouldn't be any,
Yeah.
assuming it's, a particle with its antiparticle. I mean, just any random antiparticle is not necessarily going to conserve. So suppose an electron and a positron collide head on. Both have kinetic energy of 1.16 MeV and rest energy of 0.511 MeV. They produce two photons, which by conservation of momentum must have equal energy and move in opposite directions. What is the energy of the photon? Gotcha. And you did that just by realizing since it's two, it's got to be the total energy of the mass plus the kinetic energy times two. for two
Yes,
of them,
sir.
but divide that again by 2 to get 1. Okay, yeah. So you were good. Now it's part D. 2 protons with equal kinetic energy collide head on. What is the minimum kinetic energy, K, of the proton of one of these protons necessary to make a pion antipion pair? The rest energy of a pion is, oh good, they gave you the number. Okay, so they're asking what the is the minimum kinetic energy. So what you have is total energy must be conserved. So you take the proton, which is I think 938.27 MeV is its rest energy, and you add that to the okay, so we add that to the kinetic energy of the proton, and then we add another one because it's 2 protons, and then we add another kinetic energy, and all that must add up to the kinetic energy of the photons plus, or excuse me, of the pions plus 2 times that rest energy of the pions. Does that make sense? In other words, the total energy before has to include the rest energy of the proton, the kinetic energy of the proton, which they're asking for, plus the rest energy of the other photon, plus the same kinetic energy of the other proton, because they're going to be identical. Collide hit on equal kinetic energy. Yeah, so it's 2 kp basically, plus 2 times 638.27 MeV. That's the initial energy. And then the final energy is 2 times 139.6 plus well, that's the bare minimum because you have to have at least that much.
So go ahead.
I was just going to say, so that that would allow for conservation of energy. Conservation of momentum, if you're in the center of mass frame, could be 0, so you don't necessarily have to have them have any momentum. So it used to be that.
Okay. So you have for each proton you have 938.3 plus kp, and then that's multiplied by 2 because you have 2 of them,
Right.
then 2 times 139.6 is your on the right hand side of the equation.
Right. 139.6. I'm writing it down myself.
Okay.
So yeah, what you're going to end up doing is, and you can factor out all those 2s. I have a common factor of 2 in every term now. So you can just say, that's the same number though. And the protons are actually heavier than the pions.
Yeah.
So in actuality, they don't have to necessarily have any energy. They just have to overcome. They just have to overcome the repulsion force of the electricity and magnetism. Let me think about that a second. There's something weird with that one. Is this the same set of problems that you're doing?
This is the 43 homework.
Okay. Yeah, let me check that out real quick just to see what if anything, I'm missing. I doubt they want you to go back and consider what kinetic energy it must have to overcome the Coulomb force, but that might be what they're trying to shoot at here. That's a little more advanced problem than I normally expect them to ask in this chapter, but I'll see. Was this the first one? Do you know?
Problem 4 of chapter 43 homework.
Oh, yeah, I see it now. Antimatter. Antimatter. Oh, okay, wait a second. Oh, you know what I was thinking, which might not even conserve baryon number and all that good stuff. I was picturing, were you also picturing these two protons disappearing and forming the proton, or excuse me, the pion antipion pair?
Yeah.
Yeah, that's not what's going on. I completely misread it because I, was sort of reading quickly. But no, the all that has to happen is the protons have to have enough kinetic energy to create the pion antipion pair. Well, the mass of the pion antipion pair is 139.6, or the rest energy is that. So really all you have to do is make sure each of those protons have that much kinetic energy. Then that's enough. So it's just a 140 or 139.6.
Yeah.
Okay.
Yeah, it completely boneheaded that one. I should have known better because two protons, I knew they weren't going to annihilate, but I don't know. I was thinking they disappeared after the fact. So that was stupid of me. Glad I checked that before I wasted more of your time and answers.
So, let's see here. One of these protons. So it'd just be 139.6 because you have two protons.
Yeah, if they told you to 3 sig figs, so you just want 140.
Okay.
Yeah, watch out for that. If you put in 139.6, they'll say, no, you're wrong. You did
Yeah,
the
I'll
wrong
get you.
instructions.
So there's 140. Okay, there we go.
Yeah.
Makes sense. Because I was getting to the same point where we're earlier. I was like, why is there like all of a sudden negative?
Yeah, that again, because we were thinking a proton antiproton, but it was just two protons, not a proton antiproton. So yeah, but luckily your instructor went down in the crash with you. So
I feel so bad.
I didn't want to say anything in case my explanation was wrong, but like I quite literally read equal kinetic energies. I'm like, yep, I've seen enough. 140.
yeah, good job. That was a nice catch.
Yeah.
Symmetry breaking occurs when the electrolytic theory at about 10 to the negative 18th meters. Okay. Find the energy corresponding to this. Okay.
I went and like started researching the electroweak force and stuff, but I still didn't quite get it.
I think they're wanting you to use that like a wavelength. I don't remember them talking about this in there. And there's I mean, I'm sure they did, but there's a symmetry issue, a supersymmetry, and all this stuff that they call it symmetry breaking, and that's what I'm kind of looking for right now. Let me see something. Make sure I follow what's going on here. I'm pulling up so I can read the question myself. I sort of read the blue box, and that was sometimes that gives you a necessary hint. Yeah, there's nothing. I didn't miss anything on that. It just said symmetry breaking occurs in the electroweak theory at about 10 to the negative 18th meters, and then they ask us to find an energy corresponding to this. So what? Oh, it didn't even ask you. It didn't even tell you what units it wanted.
Yeah, you can come up with the units.
So yeah, let's see. I want to try something right now. So I'm gonna look at in something really quick in chapter 43 on this, just to double check. I want to look where they actually showed us the electroweak. Okay. I'm thinking what they're wanting us to use here is that your calculation of the change in kinetic or the uncertainty in the energy is multiplied by the uncertainty in time. But you're assuming that the particle interchange is going to be something traveling very near the speed of light, so you can get a time for that. So let me show you what I'm thinking is going on with this. So you say 10 to the negative 18th meters. What I think we're saying here is delta E, which is what we're looking for, times delta T is greater than or on the order of H bar. Remember, H bar is H over 2 pi. So we know that distance is equal to velocity times time, so that time is equal to velocity over distance. So we could say delta T is equal to C over, let's call this D. And then you'd say, okay, well, delta E times C over D is greater than or on the order of H bar. So you'd say delta E is on the order of, let me check this real quick. This doesn't seem right now. HD over C. Yeah, that might be. Let's see. So we're looking at, oh, H bar. So we're looking
Can
at
you
6.
scoot your paper up a little bit?
Thank you. No problem. Can you see it now?
Yeah, I can see it. Thank you.
No problem. 6.626 times 10 to the negative 34th joule seconds times 1 times 10 to the negative 18th meters times 3.00 times 10 to the 8th meters per second. And then I got to remember the 2 pi, of course. And then I'll have to convert that to electron volts and giga electron volts or mega electron volts, whatever's fitting. So 6.626 e to the negative 34 times 1 e to the negative 18 divided by, I'll use my parentheses, 3 e to the 8th times 2 times 3.14159. Oh, okay, that gives me 300. Well, that can't be it. 6.626, 10 to the 18th. This, that's 351.5 times 10 to the negative 63. Yeah, I missed something on this. This can't be right. That's joules. Yeah, that's not right at all. I can't even find anything on symmetry breaking right here. And I didn't even know this question was in here because I've never taught anything about symmetry breaking. Let me double check. Maybe they give us some hint of that inside of the body of the text that I just rolled over and didn't pay attention to. Symmetry breaking. Yeah. Well, you know, one question is not going to be on the final.
Yeah, thankfully I ended up requesting this answer as well.
Did you?
Yeah.
Did they give you any explanation of it about why they did it or anything? Because everything I could think of is not something that I could teach here.
Yeah, it like I requested, it just gives me the answer. It doesn't even give me like the hints or like how to get there. Yeah.
Gotcha.
Just very blunt with it.
Yeah. While I'm in mastering, let me I'm going to pull up my ebook real quick and do because with the ebook you can actually do a search for a particular word, so that's kind of helpful. So I'm going to pull that up real quick and see see if I see it. See, when we learned about symmetry breaking, we were doing these things. It was really complicated, and I'm telling you, I don't understand it well enough to teach it at this level. It's not that it can't be taught at this level. It's that I don't know enough about symmetry breaking to teach it at this level. So, you know, I might pull up my old memories of what we did in grad school in my advanced quantum mechanics class, but I wouldn't know how to bring it down to decent words. And even then, I don't remember off the top of my head how we did it. I just knew that symmetry breaking was, well, it all had a lot to do with matrices multiplying by each other that were called like Lie algebras and all that good stuff. So just an SDMS is one of those things where you know, take the class, you do the homework, you learn how to solve problems, and you feel like that's as close as you're ever going to come to understanding it, is just being able to solve problems, and even that a lot is just poking and hoping. But that does happen, and I'm definitely in that predicament right now. Symmetry breaking occurs in electroweak theory at about 10 to the negative 18 meters. I wonder what is. I'm going to calculate the Coulomb energy of basically 2 electron charges. Okay, there we go. 2 electron charges being 10 to the 18th, 10 to the negative 18th meters apart. And that's as close as I can think of what they're meaning here. Symmetry breaking. Another thing is that's a point where a symmetry exists that makes those forces equivalent. Remember when I talked about the standard model? They said that they were able to, or I said that they were able to take the strong nuclear force, the electromagnetic force, and the weak nuclear force, and show that they were all different sides of the same coin.
Yeah.
When they become separate, that's the actual act of symmetry breaking. So I'm thinking it might still need to be do that, but let's check. Okay, so that's a good sign. I did the word symmetry and it has nothing in the textbook. Let's look for. Here he is. Normal larger distance is referred to as symmetry breaking. Okay, so I found something. I'm looking for where that is. Oddly, I did a search for symmetry and it didn't come up with anything, but I did a search for breaking and it came up with 2 things. Is that crazy? And right in front of the word breaking is the word symmetry. So what happens between a unification distance of 10 to the negative 31 meters and more normal larger distances is referred to as symmetry breaking. As analogy, consider the atom in a crystal. I'm looking on, I don't even know what page number it is. It's section 4311. It's the beginning of the 3rd paragraph. Well, 1, 2, 3, 4th paragraph, sorry.
Section
4311.
Okay. Also found an article online, like a PDF, that
Well, I know the answer. I mean, I've seen the answer, but it doesn't make any sense to me to give that. So I mean, I'll give that. It's not a problem because I can't solve it right now, but I'm trying to figure out what I missed. I remembered reading all this section, but in the simplest form of gut, the theoretical estimate of your proton mean life for decay is this is about 10 to 31 years, and this is now within the realm of testability. Proton decays have still not been seen, and experiments put the lower limit on the proton mean for 10 to the negative or 10 to the 33 years. This may seem a disappointment, but on the other hand, it presents a challenge. No, they're not going any further with symmetry breaking on that discussion anyways. That was page 1187 was where that paragraph was, and I just read the top of page 1188. Let me see if something's on 1189 to make sense of it. Oh, I think I just saw something at the bottom of 1188. But my light speed computer is not handling that well. Yeah, there's nothing here. So let's look over there again. Just at the bottom of page 1188, I think I saw something that said symmetry breaking. Man, I must have phased out when I was reading this. Okay, asymmetry was broken. So that's the last paragraph. It says, an interesting prediction of unified theories relates to cosmology. It is thought that during the first 10 to the negative 35th seconds after the theorized Big Bang that created the universe, the temperature was so extremely high that all particles had energies corresponding to the unification scale. Baryon number would not have been conserved, then perhaps allowing an imbalance that might account for the observed predominance of matter over antimatter in the universe. To the fact that we are surrounded by matter with no significant antimatter in sight is considered a problem in search of an explanation. See also chapter 44. We call this antimatter matter antimatter problem. To understand it may require still undiscovered phenomena, perhaps related to quarks and neutrinos or the Higgs boson or supersymmetry. The last example is interesting, for it illustrates a deep connection between investigations at either end of the scale. Theories about the tiniest objects, elementary particles, have a strong bearing on the understanding of the universe on a large scale. It says 4319 is a rough diagram. Yeah, so that's where all the particles or all the forces are identical before they start to split off. So you can see gravity splits off really early, but in that line on the figure in 4319, basically everything's unified except for gravity until it gets to that break where it goes to strong and electroweak. Electroweak and strong are electroweak, meaning the electromagnetic, and the weak are still together after that, but the strongs broke off. And that scale down here on the bottom is in energies. So is a rough diagram integrating the four fundamental forces in nature condensed out. A symmetry was broken as time went on after the Big Bang, and as the mean temperature of the universe is typical. So that's 10 to the negative 11 seconds, and those are all energies and relative strength. And they said the electroweak broke off at 10 to the negative 18. Was that the scale? Yeah. Yeah, that doesn't give me anything to help me on that. And they said the next example. Let me look at that next example again. I didn't see anything useful on that. I'm sorry I don't know this better. This is really bad.
Oh, you're fine.
Well, that's another thing I gotta learn. I got to break out my elementary particles textbook again and start reading that. Yeah, there's no example here. They didn't do an example like they said they were going to. Okay. And yeah, that's absurd. Okay, let me check one more thing real quick, and hopefully this will be it. I have a place where I keep my notes when I'm actually working out problems on this textbook. So I'm going to pull up the last time I did a job for them, which was almost 10 years ago, I think. I did their website, and I'll see if I can find my notes about if I solved that problem.
Is the answer somewhere around 1 tera electron volt?
No, it says it's 200 GeV.
Oh, okay.
What was making you think the tera electron volt?
There's an article I was reading online. It was talking about yeah.
Yeah, I'm pulling up. I just found my handwritten notes for chapter 40. I think it was 42 then. Plus this looks like elementary particles. I flip through that real quick.
If anyone has grade or subscription to that, they have the answer on there and the description
Of what, honey?
on why. I don't have
Okay,
that.
thank you.
All right.
Okay.
What service was that, DJ?
Numerade.
Yeah, I don't have that.
Yeah.
I don't really have anything.
Yeah, no, I've been very tempted to like get Chagger or something like that, but honestly, I'm just too cheap to. So,
Well, like
yeah, it's not as helpful as you think either.
Yeah,
It's,
it really isn't.
Chegg
And
mostly
especially with
takes those
Chegg.
instructors manuals and makes those available. And sometimes instructors have a hard time making sense of the instructor manual. Just because sometimes they just leave out a lot of steps, and unless you've worked that particular problem before, it can be a nightmare.
yeah.
Okay, now it's finally opening. It's going very, very slowly, but it's opening. Okay. That's evidently what I did was sort of the same thing I'm doing here with the uncertainty principle, but then I'm supposed to take that and set that equal to MC squared and find out the rest energy of it. But that's what I wrote down in my notes. Like I really knew something back then. Oh, I'm so old. So let me revise what I was showing you. I can fit it right here. Are you looking at my document cam right now?
Yeah, I can see it.
Okay, so what we're saying is we want to find the rest energy of basically the same thing we did here. Remember, we had h bar, which is h over 2 pi, of course. We had h bar times, I thought I had c over d. Yeah, I did have c. Oh, I had d over c. Did I make it just a stupid arithmetic error?
No, I think it
Yep.
should be d over.
Yeah, that's exactly what I did wrong. So I was right this time. MC squared equals delta E is equal to, that was the problem, H C over 2 pi D. And that's, in other words, I did it right initially. but that
Okay.
whole algebra made me mad.
Oh, because you had.
I had D over C
Okay.
instead of C over D. So now we can work that out. Let me work out the numbers. You know what I'm going to put there. I'm just going to put this and this in a different order. So 6.626 e to the negative 34 times 3 e to the 8th. See, Mimi? Divided by parenthesis 2 times 3.14159 times 1 e to the negative 18. If I would have looked at the units, I would have known that didn't work out. I got 31 times 31.63, actually 64, times 10 to the negative 9th joules. And if I divide that by 1.602 e to the negative 19th joules per electron volt, I get 197.4 times 10 to the 9th EV, which does look like 200 electron volts.
Okay.
So yeah, my Hammond and Holland, I was actually right with the Heisenberg uncertainty principle. I just did the algebra wrong because I'm a crackhead, I guess.
With the Heisenberg uncertainty principle, the delta E and delta T, that's the uncertainty. So it's not, that's like saying we don't know the energy to this degree.
Yeah, that's the weird part about the uncertainty principles. Those deltas are technically supposed to be standard errors or standard deviations. Basically, that's how we calculate them formally to get the result. But because that is the possibility of error, you can use it other ways. So what they're saying is because this and this is greater than h bar, what that means is you can have an uncertainty in your energy times an uncertainty in time that's right at h bar. And in that sense, you're allowed to violate conservation of energy. So when they say the scale is 10 to the negative 18th meters, what you're imagining is a particle is going to come out of existence, come out of nothingness into existence, and it's going to travel for a distance of 10 to the 18th meters. But that's a violation of conservation of mass energy. We just literally pulled mass / energy out of the air that we didn't have the right to do because there was no energy to supply it. But as long as that is an experimental uncertainty, then as long as it don't happen for a time longer than delta T given by this, then you haven't violated anything.
Is it that you haven't violated anything, or is there's no measurable way to know if you violated anything?
Yeah, that's sort of the crux. Yeah, you can sort of, that's why you're allowed to treat it that way, because there's no way you could ever detect it. So it's sort of like you can break the laws of physics as long as you're not doing it in such a way that it's measurable or something. So that's another way of thinking about it. But sometimes also, like if you do delta P, the other uncertainty principle that you're used to is delta X, delta P sub X is greater than or on the order of H bar. So this actually is kind of weird because delta P is X is really a scalar quantity, and you don't really think in terms of negative P's. That just means in the opposite direction. So if you get a delta P that's kind of big, that forces the particles to have a kind of big velocity because the smallest end of P is 0. So if you got an uncertainty of 3 GeV per C, then that means your particle can actually be accelerated to 3 GeV per C in momentum. So sometimes this delta is like the smallest thing it can be, because it can go down to 0, or it can go as high as the other end of the delta P, which, like I said, if that happens to be 3 GeV per C, then yeah, that particle can, by compressing it into a smaller and smaller area, you can force that particle to reach a momentum of 3 GeV per C. So there's a lot of little weird ways you can apply it. And that's what's going on here is basically you have a particle running along, it emits a virtual particle. That virtual particle can only travel 10 to the negative 18 meters. And therefore, that's going to take a certain amount of time. You take the distance 10 to the negative 18 meters, divide it by roughly the speed of light, and that gives you how long it's going to be in existence. And if you set that, then that's how much energy violation you can do, and hence you get 200 GeV.
Okay, so I just want to make sure I understand this correctly. So you're that delta E times delta T equals H bar. H bar is H over 2 pi, and H is Planck's constant.
Right.
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 Okay. So then that means that you can have a particle with a certain energy exist for a certain amount of time and it not violate any laws just because we can't measure things accurate enough.
Right. By understanding the uncertainty and the time is along with the uncertainty and the energy, since they have to be greater than or equal to H bar, it can be violated for a temporary time, long as that expression is there. Yeah, it's weird. And that's the whole nature of these particles, where we're talking about gauge bosons. Gauge bosons only exist because of that. If it wasn't for that law, we would have never thought of gauge bosons. And then now it turns out that gauge bosons do exist, and we've measured them, we've created them, but it was all a hypothesis based on that uncertainty principle.
Oh, so it's not just like Heisenberg's uncertainty principle isn't just a way for us to kind of get errors to like account for error in our measurements. It's like actually also describing physical properties. Like,
yeah, that's the big takeaway from it is Heisenberg's uncertainty is a real physical limitation, period, no ifs, ands, or buts about it, which means, yeah, that accounts for experimental error, but it also accounts for reality.
So like the laws of the universe, it's a law of the universe, not just something that we came up with to account for some.
Exactly. And it made perfect sense. And not in Schrodinger's, it took a little while before it made sense, but in Heisenberg's way he did it, which was really so abstract, it literally took me like 2 years to understand. But it's so abstract, but this is a natural result. These two uncertainty principles are obvious from Heisenberg's way of doing quantum mechanics. In Schrodinger's, you actually have to take the wave function and calculate the expectation value of x squared minus the expectation value of x, but squared. So you sort of sum up all the x squareds and then average it, and then you subtract from that the average of x and then square it. That's what I mean by it being a sort of a standard deviation. And you do that with a big integral, and that's how you calculate delta x. Then you calculate delta p the same way, but using it for p instead of x, and that actually gives you a product that shows it can be only greater than or equal to h bar because of actually the triangle inequality. So it took a little work, but you had to geometrically realize, oh, this is the triangle equality, basically saying that the sum of two vectors cannot be bigger than the sum or any smaller than the difference. So that triangle inequality is what makes this come true. So it's like it took a while, but you literally just had to do a few integrals and you'd see that it pops out. That's one of the things you do in either an advanced undergraduate quantum class or a undergraduate or a graduate quantum class.
Okay.
But yeah, it is a fundamental idea of nature that we can't get around. No ifs, ands, or buts about it.
Huh. That's really cool, actually.
Yeah, it's not easy to think about, but once you start thinking about it, you're like, wow, I'm starting to see something deeper and understand something a little deeper.
Yeah.
But I don't recall ever hearing that called symmetry breaking, but I understand in retrospect that that you could consider it that way.
Yeah.
Anything else?
That was the last question I had.
Okay, well, at least we got you through that one. David Parsons, did you have any other questions?
Nope. Just one I had about the test. That was it.
Gotcha. And that 200 GeV is the same thing you got when you asked for the answer?
Yeah. Well, when I requested it, it said, let me make sure. Let's go course down. Yeah, 200 GeV.
Yeah, that's it. So yeah, just remember that's a fairly easy calculation to do. So watch out for that if you're asked to get some energy based on a time or based on a distance. It's almost certainly going to be one of these scenarios. Or if you're talking about virtual particles, it's going to be this scenario. Okay, that's just how we did. And I did that for the Yukawa force. Remember what is his name? I can't remember his first name. Hideki Yukawa. He predicted the existence of a particle that would represent the weak nuclear or the strong nuclear force. No, it was the weak. That's right. And we got an estimate of the mass, and we later found it, but it turned out not to be the right gauge boson, but it still was found as a pion.
Huh.
So, anything else, anyone?
That's all I had.
No
Yeah.
problem. And remember, you just got this one test. If you are doing these homeworks, you're in a lot better shape than necessary. I tried to be very selective about the test questions I put in there for 43 and 44. And so hopefully that'll still be pretty easy for you. So knock that out, and you've got more than enough information about 14 and 15 for the final, because that's really the final is going to be on 1 through 11, 36, 14, 15.
1 through 11, 36, and 14.
14 and 15. Yeah.
Yep.
I'll write that down.
Okay.
1 through 11, 14, 15, and 36, if I wanted to keep them in order. That's the worst looking 14 I ever wrote in my life. Like, break out the crayons, Mr. Younger. There you go. So yeah, that's what the final's on. I'm leaving out the 43 and 44. As you can see, there's I hardly ever get to teach 43. I never get to teach 44. So that's why I'm not quite as up to snuff on the 43. But hopefully I'll be able to do more, and over time I'll become a good teacher. We can all hope. I don't like you laughing. All right, well, I have another one of these at 1 tomorrow, so feel free to come by then if you like.
1 o'clock?
Yep.
Okay.
All right.
All right.
Awesome. Thank
I'm
you.
just gonna hang out here and prepare for my next class, I reckon.
Sounds good.
All right.
All right, see you guys.
See you guys at 12:30.
See you.
See you then.